Okay, so we want to start with the Planck Law now, and then derive an expression for the total energy that an object emits. So what we've got so far is total energy that goes into a cone of solid angle within a certain frequency range is given by this Planck function here. So this is the watts of energy per unit area of surface, per unit steradian of solid angle, and per unit hertz. But of course, we said earlier, we slipped this in earlier, that that's only really true for normal incidence. If you're at an angle theta, it actually gets reduced by a factor of cos theta. That makes sense, because if you're looking at an angle theta, then that little bit of area that you're looking at is actually reduced, right? If this is area dA, then the actual perpendicular area, or the effective area, is just dA cos theta. So you're essentially looking at less surface, so you're essentially going to get less radiation when you're at an angle. So this is the correct form of the Planck equation for all angles. So what we want to do now, though, is we want to add up over all solid angles, and then over all frequencies, to get the total watts per meter squared of energy coming off of the object. So that is going to be the integral over all frequencies, and then we're just going to integrate over the hemisphere. So that is from phi is 0 to 2 pi, and from theta is 0 to pi over 2. So those are our limits. So we've got epsilon, the emissivity, 2h, f cubed is a variable, c squared is a constant. Then we're going to have, we're going to badly run out of room here, 1 over the exponential, hf over kt minus 1. Then we've got the cos theta term. And then we've got a term for the Jacobian in spherical coordinates. So we're integrating over the sphere here. And, sorry, I'm just trying to move this over to give myself a wee bit more room. And it's still not going to let me. Come on, don't be so frustrated. There we are. Now I can fit it in. And the Jacobian little area element in spherical coordinates is sine theta d phi. And then, of course, we also have df. It's df at the end there for the frequency integral. So this is the tiny little element of solid angle. So, first of all, the d phi angle is trivial, and it just gives you 2 pi. And then we can pull out all the other constants, the epsilon, the 2h, the c squared. And then for our theta integral, we've got sine theta cos theta. I'll just rearrange those a little bit. Sine theta cos theta d theta from theta is 0 to pi over 2. But of course, that's like a u du. So it just ends up being sine theta squared over 2. And sine theta squared over 2 at pi over 2 is a half. And then it's 0, so this integral here just boils down to a half, because it's sine squared theta over 2. So the only real difficulty we face is this frequency integral. And it's a significant difficulty, because we've got frequency cubed df. Well, that part's not too bad. But then the frequency also appears in the exponential function. Oh my. Well, we're going to make a substitution. We'll let x be hf over kt. That means the frequency is kt over hx. And df is kt over h dx. So having made that substitution, first of all, this half will cancel out this 2 here. And so we're left with some constants out in front, namely 2 pi h epsilon over c squared. Then we're left with this integral. Now as f goes from 0 to infinity, x will go from 0 to infinity. So we had f cubed, so that's going to be k cubed, t cubed, over h cubed. X cubed df is kt over h dx. And then it gets a little better because here we just have 1 over e to the x minus 1. So when we pull all the constants out, we've got epsilon, then we've got 2 pi k to the 4, temperature to the 4th, over h cubed c squared, and then times the integral of x cubed dx over e to the x subtract 1. Now we want to do something with that integral. Basically, this is just a number, though, so we see that our intensity varies with 4th power temperature, and that fundamentally is the Stefan-Boltzmann law. We just need to evaluate this integral so we know what the constant is. Well, 1 over e to the x minus 1 can be rewritten this way by multiplying through by e to the minus x each term. And that is the sum of this geometric series from 1 to infinity e to the minus nx, because if you remember your geometric series theory, you know that the geometric series sum is the first term over 1 minus the common ratio. The first term at n equals 1 is e to the minus x, and the common ratio of this series is e to the minus x. So we can replace the integrand, which is this or this, with this infinite sum. And that's what we've done down here. Now, we can switch the order of the summation and the integration. And so now we want to know what is the integral of x cubed e to the minus nx dx. And we're going to do that integral by parts, because when we make this u dv, in the next step it'll be du, and then that makes this power of x1 smaller. We then do that repeatedly. So this is u, this is dv, it's uv minus the integral of v du. Now the uv term we evaluate between 0 and infinity, and it just gives us 0, because the exponential function dies at infinity, and this part dies at 0. And you see that we have indeed made it one smaller. Now we're integrating x squared, but we have this constant term out in front. This again we do by parts, and that takes us from an x squared integral down to an x integral. And we get this term of 2 over n in front. And that's just from, if this was dv, then when we integrate that to get v, we pick up these terms like that. So again, by parts gives us this expression. This disappears, so now you've got 6 over n squared times the integral of x e to the minus nx. Again, we do that by parts, and now we're up to 6 over n cubed. And finally, an integral that we can actually evaluate. This works out to e to the minus nx over n from 0 up to infinity. And, oh, with the minus sign. The minus sign right here. And now we just need to put in infinity, put in 0, and subtract, and that just works out to be 1 over n. So it's 6 over n. Oh, sorry, it's down here. Oh yes, I had evaluated it already. Isn't that nice? Yeah, so that's just 6 over n cubed, and then it is 0 minus 1 over n. So it's 6 over n to the 4. Okay, so that was the integral, but of course we've got to put that back inside the summation, so we end up summing this over all values of n. So where we are now, is the following. So we've got 2 pi k to the 4, t to the 4, emissivity, over h cubed c squared. And then we've got now this summation, 6 over n to the 4. So we'll pull the 6 out, and then we just have to sum 1 over n to the 4. Well, that you'll do in a later math course. It works out to be pi to the 4th over 90. So we now have, again, it's 2 pi k to the 4. We had a 6 in the summation, a pi to the 4 from the result of the summation over 90. And then we had h cubed and c squared. And then all of this was times the emissivity and times the temperature to the 4th power. So all that stuff at the front is a constant, so we're going to call it something. It's sigma, Stefan's constant, and it depends on all of this, and there's a 90, a factor of 90 that may be missing from that. And now we can work that out, see what that constant is. So K is Boltzmann, 1.38 times 10 to the minus 38 joules per Kelvin to the 4th power. Then we have 6 pi to the 4. What are you doing? That's not right. Where did that come from? It's 1.38 times 10 to the minus 23. And then in the denominator, we've got 90. Then we've got Planck's constant, 6.63 times 10 to the minus 34 joule seconds cubed. And then we've got 3 times 10 to the 8th meters per second squared. So if you work that all out, it ends up to be 5.67 times 10 to the power minus 8. You're going to have 1 joule that survives from joules to the 4th over joules cubed. And then you're going to have the per second that survives here in the denominator. So that gives you the joules per second. That gives you per Kelvin to the 4th. And so the units are watts per meter squared, Kelvin to the 4th. And the meter squared comes from here. So our intensity then is given by sigma epsilon t to the 4th. I guess I don't need to write it again, where this is the value of sigma. Now that's called Stefan's constant. But we're not done yet, because intensity is a ratio of power to area, watts per square meter. So the power will be the product of the intensity and the area. So this is watts per square meter. So the total power coming off our hot object is there for the intensity, sigma epsilon t to the 4th, times the area of the object. So this is now the watts that's emitted by the object. But of course, not only does the object emit thermal energy, it also absorbs thermal energy from the surroundings. And the amount of emission from the surroundings depends on the surroundings temperature to the power of 4. But the amount of that actually hits the object depends on the area of the object. So we end up then, for the net power, which is going to be the amount that's emitted minus the amount that's absorbed from the surroundings, is sigma epsilon area object temperature to the 4th minus surroundings temperature to the 4th. And this is known as the Stefan-Boltzmann Law. And we got it by integrating the Planck function. First over all solid emission angles, that wasn't so hard, and then over all frequencies. We see that the amount of power coming off the hot object varies as temperature to the 4th. Now, let's do some simple examples. Okay, so here we have a student out sunning themselves, and it's on a cool day. So what's happening? Well, they're going to be emitting thermal energy to the surroundings. So we have watts per meter squared Kelvin to the 4th. That's the Stefan's constant. The emissivity of skin. Skin is a very good absorber and emitter at infrared wavelengths, which is where thermal energy is mostly coming from. Now, the skin temperature is 34, so that's 307 Kelvin to the fourth power. And then the environment's 20, so that's 293 Kelvin to the power of 4. So we see dimensionally, meters squared cancels. There's Kelvin to the fourth here. In both of those terms, it's going to cancel. And we end up with the radiant power in watts. The answer is 115.8. So that's the loss to the environment. Now, if the student happens to be in the sun, then they're going to be absorbing energy from the sun. And as we'll see shortly, the solar intensity is about 1,000 watts per square meter. So every square meter, and this would be on a really intense sun day with, in July when the sun is almost directly overhead. And there's about 1.5 square meters of area that's exposed to the solar energy, but then not all of that is absorbed by the skin. The emissivity tells us how much is actually absorbed. So the solar input power then is the solar intensity times the area times the fraction that's absorbed. It's 1,000 watts per square meter times 1.5 meters squared times the 0.9. And that is, let's see, 1350 watts. So the net, when they're in the sun, is going to be 1350 that's absorbed minus the 115.8 that's actually being radiated to the environment. So there's about 1234 watts absorbed, and this student's going to be heating up if they're out there on a sunny day. Now, where did we get that 1,000 watts? Well, 1,000 watts per square meter. Here's where it comes. Here's the sun, and then a distance r away, 150 million kilometers, is the Earth. And the Earth orbits the sun in roughly a circle. Really, it's an ellipse. And the sun's emitting this much power. So that power gets spread out over the surface of a sphere. And to be a bit sophisticated, we could call it a heliocentric sphere, centered on the sun. So the solar intensity anywhere on this sphere is that energy of the sun has been spread out over its surface area. So there was 4 times 10 to the 26 joules each second emitted by the sun. By the time you're 150 million kilometers away, that's been reduced down to about 1,400, well, I guess it's 1,415, calculated, watts per square meter. So how did we get the 1,000? Okay, so we're here on the Earth, and then up here, at what we call the top of the atmosphere, it's about 1,400 watts per meter squared. But down here on the surface, it's been reduced to 1,000. And that's a typical maximum, even when the sun's directly overhead. And the reason for that is atmospheric gases absorb a certain portion of this. There's also reflection off of aerosols, reflection off of clouds, etc., etc., etc. And a typical drop is from about 1,400 down to a maximum of 1,000 at the surface. So now let's park a black car in the hot sun and say that there's a couple of square meters of absorbing area there. And so we've got our 1,000 watts per square meter of solar energy on a hot summer day. You know, this number would drop during the wintertime as the sun dips low in the horizon, and obviously it drops to 0 at night. So there's a lot of variation. But let's say it's out in the hot sun. Now, so the car is going to be absorbing energy from the sun, and it's going to be radiating energy according to the Stefan-Boltzmann Law. So the solar input as we said, will be the intensity times the area times the fraction that's absorbed. So there's 1,000 watts per every square meter, there's 2 square meters, and then there's a fraction 0.95 that's actually absorbed. Now the radiated output, the infrared output, is given by the Stefan-Boltzmann Law, and that depends on the car temperature to the fourth minus the environment surroundings temperature to the fourth. Now that these two have to balance, they will be balanced at equilibrium. I don't have quite enough room there. So I'll squeeze it in over here. So once the car reaches steady state temperature, the input from the sun must be balanced by the output, the radiation escaping from the hot car. So if we just set those things equal to each other, and by doing so we're ignoring convective cooling, we're saying the car is only cooled radiatively, we see that these things cancel, and then we divide both sides by the Stefan-Boltzmann constant, or Stefan's constant. We add environment temperature to the fourth. This gives us car temperature to the fourth. We take the fourth root to get the temperature of the car. So with an intensity of 1,000 watts per square meter, Stefan's constant of 5.67 times 10 to the minus 8, and the environment being at 293 Kelvin, we find that the car temperature is 398 Kelvin, or a nice comfortable 124 C. Now, given that's over the boiling temperature of water, that's probably not realistic. So, if we want to get something a little more realistic, well, let's allow the car to cool convectively as well. Then when we write our balance equation, yes, we'll have the radiative loss of the car to the environment, but we'll also have, there we go, fit, a convective term. So this is the radiant output, and this is the convective output. Now, unlike the previous equation, sorry, this is the solar incoming. Unlike the previous equation, this one doesn't solve easy because it's a t to the fourth and t term in it. So I actually typed it into an equation solver on Wolfram Alpha, and I got a temperature then of 348 Kelvin for the given surface transfer coefficient of 10. Now that's down to about 75 C, and that's not unreasonable. You know, car temperatures definitely reach, some pretty intense temperatures very quickly, which is why pets and small children and elderly people have perished in these environments. So this takes us to the end then of our pre-lecture. So what we did is we started with the Planck function, our B function, and for frequencies it was 2hf cubed over c squared 1 over e to the hf over kt subtract 1, and then we said there had to be a cos theta term in there. So that's the radiant energy per unit solid angle, per unit frequency at an angle theta. And then we integrated that over a half sphere, over a hemisphere. So we said, okay, there's a hot surface here, and we want to integrate and find all of the radiation going in all of that half sphere over all the possible frequencies that this hot object could be emitting, and that took us to this new law, the Stefan-Boltzmann Law. Sigma epsilon area temperature of the object to the fourth minus environment temperature to the fourth. Now, there's going to be times when you'll want to use the Planck function, and going to be times when you're interested instead of the total energy that's being emitted. Now, we're going to do a little experimental test of that fourth power law using a Leslie cube, which is just a hot surface, and a thermopile, which captures all the radiation coming off the object. And then we'll do some problems related to thermal energy transfer. But this completes the theory, anyway, for our heat transfer section and for our second unit on ideal gas and the first law of thermodynamics.